Welcome back to the part 5 and the last part of lecture 2. In this part, we will talk about feature selection, also known as variable selection. Suppose the feature space has p many features, that is x is x1, x2, xp, there are p features and p is very large. Then we would like to drop some of the features which have no impact on the target variable or the dependent variable y. So what we want to do, we want to develop a model y as a function of x1, x2, xq, where q is way less than p. So suppose you have 2000 features, but you want to build a model with only 15 important features which has an impact on y, and you don't want to use the other features, which is basically white noise. And this is a very standard technique. The advantage is, if you build the model with all 2000 features, then your model complexity is too high. Explaining such model is very difficult. But if you build the model with 15 features, then it is very easily at least better than 2000. It's still at the 15 dimension geometry, but it's better than 2000 dimension geometry. So in that sense, we would like to drop some features, or we would like to select the features which have effect on y, and we would like to ignore the features which does not have effect on y. So in that way, what we can do, we can try something called best subset selection. To perform best subset selection, we fit a separate least square regression best subset for each possible combinations of p predictors. That is, we fit p models containing exactly one predictor, then all p choose 2 PC2 or P into P minus 1 by 2 models that contain exactly two predictors. Then we can fit all models that are actually have three predictors, all possible combinations, and we can keep doing it. In that way, the model size of the model space turns out to be 2 to the power p minus 1, because you don't want to, you want to, I mean, in a model, either a feature is there or you want to drop the feature. So there are two possibilities, either it is there or it is not there. So as a result, there are 2 to the power p possible models, but no features is there. We don't want to consider that, we want to drop. So that's why 2 to the power p minus 1. Now, how, if I ask you to implement the best subset selection, how can you do that? How can you implement that? So let M0 denote the null model, which contains no predictors. Basically, y equal to intercept plus epsilon. This model simply predicts the same mean for each observation. So intercept is the mean of y values, and that's it. That will be predicted for all the observations for x's, or uh, for k equal to 1 2 dot 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 p, fit all pck models that contain exactly k predictors. Then you pick the best among these pck models and call it mk. So that model is the best model among the all possible models which contains k predictors. Here best is defined as having the smallest residual sum of square, or equivalently largest r square, or you can use mean square error, or you can use AIC or BIC criteria. You can choose whatever criteria, but once you choose the criteria, you stick to that model selection criteria. Then you select a single best model among M0, M1 to MP using cross-validated prediction error using AIC, BIC or adjusted R square. So though the step 2 identifies the best model on the training data for each subset size in order to reduce the problem from one of the 2 to the power p possible models to one of the p plus 1 possible models. The best subset selection involves fitting of 2 to the power p models, and that actually a severe problem, because if you have say p equal to 20, that means you have only 20 features in your data set, which is a very moderate size in today's, you know, probably will consider even a small data problem. Base subset selection algorithm requires fitting 1,048,576 separate models. So it will take a long time to fit all the models and come up with the best model. If you can fit best subset selection, that is the best model, that is the optimal model. But it's very difficult. This means base subset selection is almost not possible unless it is a toy or small data set. So what people have done, people have come up with some shortcut or come up with something, a little greedy algorithm called forward stepwise selection. So what it does, you start with the null model, M not null model, which contains no predictor. Then you move on from 0 to 1 to p minus 1. Consider all p minus k models that augment the predictors in mk with one additional predictor. So if you have chosen say x3 in the first iteration, in the second iteration x3 will default, by default it will be there, it will, and then you will choose among the x rest of the a predictor among the rest of the predictors other than x3. Suppose now you choose x7, then in the next iteration x3 and x7 will be there no matter what, and in that iteration you will choose between the rest of the predictors. So that's how it goes. So that's why it's called forward stepwise selection, and rest of the things goes exactly same as the base subset selection. In this case, in the forward stepwise selection, what happens, unlike base subset selection which involves fitting 2 to the power p many models, forward stepwise selection involves fitting one null model along with p minus k models in the kth iteration. This means the total amount of models that you have to fit is basically 1 plus p into p plus 1 by 2 models. So if you have, there is a substantial improvement. Now if you have p equal to 20, then base subset selection requires fitting of 1,048,576 models, whereas forward stepwise selection requires only fitting of only 211 models. So the algorithm complexity is order of p square, but it is reasonable significant improvement, and that is why forward stepwise selection or general stepwise selection is very popular. People do use left and right, and it's something we can use significantly. So the forward stepwise selection can be applied even in high dimensional setting when n is less than p. However, in this case, it is possible to construct submodels up to n minus 1 only, but still you can apply it, since each of the submodel is fit using least square methods, which will not yield any unique solution if p greater than equal to n. The third algorithm that is very popular is also known as backward stepwise selection. And in this case, the difference is slightly, it instead of start with null model, it start with the full model. So the MP denote the full model, and it starts with K, and it drops a model. It will start with all the features of the model, and then it will drop a it will drop a more feature from there, and then it will pick the model which is the best basically. So you keep doing that, and that's why it's called backwards stepwise selection. Like forward stepwise selection, you can show that the model complexity or the algorithm complexity is also order p square, or you have to compute exactly 1 plus p into p plus 1 by too many models. So can be applied in the settings of p is too large to apply test subset selection. So like forward stepwise selection, backward stepwise selection is not guaranteed to yield best model containing the subset of p predictors, but it does reasonably good job. That guarantee, I have not seen any result so far which gives us a guarantee that some kind of, even probabilistic guarantee that it will give, best model, it will contain the best model with certain probability. I have not seen any result, but I'm the literature is huge. It might be there some kind of results might be exist. um, when it comes to implementation of feature selection or step using stepwise feature selection criteria, in R there is a built-in function called step in stats package which select the model using AIC criteria or in the stepwise algorithm. Several Python implementation of stepwise feature selection is also available, so you can use either step functions of the R, or you can use any of the Python implementation of stepwise selection feature selection method. Now I will stop here. In the next lecture, we will start discussion on the issue of multicollinearity. This is one of the very difficult issue. I have seen that students do struggle in this particular issue. So we will spend quite a bit of time on the multicollinearity in lecture 3 and some more issues on the predictive models. Thank you very much. Happy weekend, and have a good day.